Okay, in this lecture we're going to cover the first part of our section 3.2 material on trigonometric integrals. So before we jump into the material for this section itself, let me mention that we're going to make frequent use of some trig identities throughout this section. So there are 4 trig identities which I would want you guys to remember throughout this section. The first is that the sum of sine squared x and cosine squared of x is 1 for any value of x. Similarly, 1 plus tangent squared of x is equal to secant squared of x. And then we have these identities involving sine and cosine squared of x. First off, sine squared of x is equivalent to 1/2 of 1 minus cosine of 2x. And cosine squared of x is equivalent to 1/2 of 1 plus cosine of 2x. So making use of these trig identities, we're going to consider how to integrate functions that involve powers of sine, cosine, secant, or tangent of x, or products of powers of sine, cosine, secant, or tangent of x. So these types of integrals we will refer to as trigonometric integrals. So the first type of trig integral that we're going to consider in this section would be an integral of the form sine x to the nth power times cosine x to the mth power with respect to x. So we're integrating a product of powers of sine and cosine of x. So to integrate this type of function, we have to consider one of 3 cases. So the way that we will go about integrating this function depends on what the powers of sine x and cosine of x are. So the first case that we'll consider is the case where n is odd, where n is the power of sine x. So if we have sine x raised to an odd power, our method for integrating will be to factor out one factor of sine x. So if sine x was odd and I factor out 1 power of sine x, I'm left with even powers of sine x. And I'm going to make use of the identity that sine squared x is equal to 1 minus cosine squared of x. So since the sum of sine x and cosine squared x is 1, sine squared x would be 1 minus cosine squared x. So I'm going to use that identity to rewrite the even power of sine x in terms of cosines, and then I'm going to use a substitution. The substitution I'm going to make is that u will be equal to cosine x, and let's think about why this would work out. So if u is equal to cosine of x, then du would be negative sine x dx. So if I factored out 1 power of sine x, when I make this substitution, I see that that 1 factor of sine will cancel this factor that I obtain from the differential. Now our second case is if m is odd. So that is if we have an odd power of cosine x, then my technique for integrating would be to factor out 1 factor of cosine x so that I'm left with only even powers of cosine. And I'm going to use the trig identity cosine squared x is equal to 1 minus sine squared x in order to rewrite all of the even powers of cosine in terms of sine. And then I will make use of the substitution u equals sine x, so that du would be equal to cosine x dx. And so that extra factor of cosine that I factored out in the first part of that method will cancel nicely with the cosine x dx term that I have from the differential. Now the trickiest case is if both n and m are even. So if we're integrating even powers of sine and cosine, if neither one of these is odd, then we have to make use of the identities. Sine squared of x is 1 minus cosine of 2x over 2, and cosine squared x is 1 plus cosine of 2x over 2. So I'm going to use these identities to rewrite the even powers of sine and cosine x, all in terms of cosine, and then I can get something which I can integrate using one of these earlier cases, or perhaps integrate directly. So in order to illustrate this in a little more detail, let's look at some examples to see how this technique will work. So in our first example, we're asked to evaluate the integral, and in part A, we have the integral of sine squared x times cosine cubed x dx. So when I look at this, I recognize it immediately as a trigonometric integral. It involves a product of powers of sine and cosine. So I need to ask myself, well, which of these three cases am I working in? And I see here that I have an odd power of cosine x. I've got cosine of x cubed. So I'm working with case 2 here. In order to evaluate this, I will first factor out 1 power of cosine x. So I had cosine x cubed. So if I factor out 1 power of cosine x, I would be left with cosine squared x times cosine x to the first. So after I peel off that 1 factor of cosine, I'm going to make use of the trig identity. Cosine squared of x is equal to 1 minus sine squared. So in other words, I'm going to rewrite everything in my integral in terms of sine. So replacing that cosine squared x with 1 minus sine squared x, we obtain the following. So if I group all of my sine x terms together, by distributing, I would have a sine squared x minus sine x to the 4th power times cosine x dx. And now I can make use of a substitution. If I let u equal sine x, then du is equal to cosine x dx. So our integral that we started with if I rewrite in terms of u, let's see what we have. So we would have the integral of u squared minus u to the 4th, since u is equal to sine x. And then this term on the end, cosine of x dx, is just equal to du. And now I know how to evaluate the integral of this polynomial function involving u. Integrating each term, I would have a 1/3 u cubed minus 1/5 u to the 5th plus an arbitrary constant, or substituting u, which was sine x, back in to my answer, I have a 1/3 sine x cubed minus 1/5 sine x to the 5th plus an arbitrary constant c. So this illustrates how that method is going to work. The general idea is to try to manipulate our integrand, making use of trig identities, so that I can put it in the form where a substitution would be appropriate. So let's look at another example. In part B, we have the integral of sine cubed x times cosine x to the fourth dx. So I recognize it immediately as a trig integral, since it's an integral involving product of powers of sine and cosine x. Now, the way that I handle this integral will depend on what those powers of sine and cosine of x are. And in this example, I see that I have an odd power of sine x. So whichever trig function has the odd power, you're going to factor out one of those trig functions from your integrand. So if I factor out one factor of sine x, I would be left with sine squared x. Then I have my cosine x to the fourth, and that extra factor of sine x that I peeled off, I'll rewrite at the end of this product. Now, once I do that, I'm going to rewrite everything else in my integrand in terms of cosine. So here, I'm going to use the fact that sine squared of x is equal to 1 minus cosine squared of x. And then I have a cosine of x to the fourth power times sine x dx. Or if I group all of my cosine terms together by distributing, I would have cosine x to the fourth minus cosine of x to the sixth times sine x dx. So by rewriting the integrand in this way, I can now make use of a substitution. If I let u equal cosine of x, then du would be negative sine x dx. So let's rewrite our integral in terms of u. We started with the integral of sine cubed x, cosine x to the fourth dx. And we rewrote it in terms of sines and cosines as we had in the line above. So rewriting that in terms of u, we would have u to the fourth minus u to the sixth. And then on the end, we had a sine x dx. So if we solve for sine x dx, we could see it would be the negative of du, just multiplying both sides of that equation by a negative 1. So on the end, we'll have a negative du, or distributing the negative to our polynomial part, we would have a positive u to the sixth minus u to the fourth du. And I know how to integrate this polynomial function in terms of u. We would have 1/7 u to the seventh minus 1/5 u to the fifth plus c. Or to get my answer in terms of x, I'm going to take u, which was equal to cosine of x, and substitute back into this answer. So we have 1/7 cosine x to the seventh minus 1/5 cosine x to the fifth plus c. All right. So let's look at another one. In part C, we have the integral of cosine x to the fifth times the square root of sine x. Now we know that we can rewrite the square root of sine x as sine x to the 1/2 power. So we see that we have a trig integral where we're multiplying powers of sine and cosine of x. And I see that this first term, cosine x to the fifth, involves an odd power of cosine. So let me factor out 1 power of cosine x, and I would be left with cosine x to the 4th power times the square root of sine x, or sine x to the 1/2 power, times the extra factor of cosine x, which I peeled off from the cosine x to the 5th power. Now I'm going to rewrite my integrand, or rewrite everything in my integrand in terms of sine x, and here I'm using the identity that cosine x squared is equal to 1 minus sine x squared. Now in this problem I had cosine x to the 4th power, so cosine of x to the 4th I can just think of as cosine of x squared quantity squared. That would give me cosine of x to the 4th. So using the trig identity that cosine squared x is 1 minus sine squared x, to get cosine of x to the 4th, I would then have to square that value. And I'm left with the square root of sine x times a cosine x dx on the end. So simplifying this, I want to try to group all of my sine x terms together. So I might start by expanding this first power, or this first term squared. So expanding 1 minus sine squared x squared, I would have 1 minus 2 times sine squared x plus sine squared x squared, which would give me sine x to the 4th power, all times the square root of sine x with a cosine x dx on the end. So distributing the square root of sine x, I would have the square root of sine x minus 2 times sine squared x times the square root of sine x, which would give me sine x to the 2.5 or the 5/2 power. And then plus sine x to the 4th times the square root of sine x would give me sine x to the 4.5 or the 9/2 power. And then we've still got our factor of cosine x dx on the end. So if I make a substitution now, where u is equal to sine x, then du will be cosine x dx. So rewriting our integral in terms of u, we have the integral of root u minus 2u to the 5/2 power plus u to the 9/2 power, and then our factor of cosine x dx we found is equal to du. So we have a du on the end. And this expression I know how to integrate. The antiderivative of the square root of u would be 2/3 u to the 3/2 power. We then have minus 2 times the antiderivative of u to the 5/2 would be u to the 7/2, and then dividing by 7/2 would be equivalent to multiplying by 2/7. So since we had a constant 2 out in front, our 2 times that 2/7 becomes a 4/7. And then we are adding the antiderivative of u to the 9/2 would be u to the 11/2 divided by 11/2, which gives us a 2/11. And then we could add an arbitrary constant since this was an indefinite integral. So for our final answer, we want to express our answer in terms of x. So let's take u, which was sine x, and substitute it back in. So here I'll have 2/3 sine x to the 3/2 power minus 4/7 sine x to the 7/2 power plus 2/11 sine x to the 11/2 power plus an arbitrary constant c. All right. So let's look at some other ones. In part D, we have a definite integral from 0 to pi over 2 of sine cubed x times cosine cubed x. So we recognize this immediately as a trig integral because our integrand is a product of powers in sine and cosine of x. So in order to integrate this, we have to decide which case we're working in. And we see for this example that both sine of x and cosine of x have odd powers. So I could use either technique where I factor out 1 power of sine x or 1 power of cosine x in order to evaluate this. In either case, I'll end up with the same answer. So since we can use either approach, I think I would make use of the approach where I factor out 1 power of cosine. So I would have a sine x cubed times cosine of x squared times this extra factor of cosine x dx. So now I can use the fact that cosine squared x is 1 minus sine squared x in order to rewrite everything else except that factor of cosine in terms of sine x. So I would have the integral from 0 to pi over 2 of sine x cubed times 1 minus sine squared x times cosine of x dx. Or grouping my sine terms, I've got the integral from 0 to pi over 2 of sine cubed x minus sine x to the 5th power times cosine x dx. So from here, I can use a substitution. I will take u as sine x so that du is equal to cosine x dx. Now this was a definite integral, so if I'm making a substitution, I also need to change my limits of integration from x values to u values. So looking at the lower limit of integration, if x is equal to 0, then u would be sine of 0, which is 0. And if x is equal to pi over 2, then u would be sine of pi over 2, which is 1. So our integral, rewritten in terms of u, will be the integral from 0 to 1 of u cubed minus u to the 5th, and then our cosine of x dx on the end is equal to du. So integrating, we have a 1/4 u to the 4th power minus 1/6 u to the 6th, and we're evaluating from u equals 0 to 1. Now, since we've already changed the limits of integration from x values to u values, I don't need to substitute sine x back in for this antiderivative. I just want to plug in the indicated values for u. So evaluating at 1, I would have 1/4 minus 1/6, and then we subtract what we get when we evaluate at 0 which would be 0. So simplifying, getting a common denominator of 12, I would have 3 over 12 minus 2 over 12, so I'm left with 1/12 for the value of that definite integral. Now you could have also approached this problem by initially factoring out 1 power of sine x, rewriting everything in terms of cosine. So take your sine squared x term, rewrite it as 1 minus cosine x squared, and then make a substitution where u is equal to cosine x and proceed in the same way. And in the end, you'll end up with the same answer of 1 over 12. So this shows one example where if you have both an odd power for sine and cosine of x, you can use either approach. So in our last example here, part E, we have the integral of sine squared x times cosine squared of x. So we recognize it immediately as a trig integral, and this is the tricky case where both the power of sine and cosine of x are even. So in this case, we cannot proceed by factoring out 1 power of either sine or cosine, but instead we have to make use of the trig identities that I had mentioned a bit earlier in this lecture. In particular, we're going to rewrite sine squared x as 1/2 of 1 minus cosine of 2 times x. And cosine squared of x is equal to 1/2 of 1 plus cosine of 2x. And then we still have our dx term on the end. So let's see what we can do from here. I'm going to start by grouping my constant terms. So here I had a 1/2 times 1/2 is 1/4. And that constant factor of 1/4 I'm going to bring out in front of my integral. And what I'm left with is 1 minus cosine of 2x times 1 plus cosine of 2x. dx. So if I expand this product, 1 minus cosine 2x times 1 plus cosine 2x, I have the following. I would have a 1 plus cosine 2x minus cosine 2x, which cancel one another, and then I would have a minus cosine of 2x squared. dx. So this new integral that I'm left with, notice that it involves an even power of cosine. So I could make use of the same sort of trig identity that I did at the beginning of this problem, or if I see that my integrand is 1 minus cosine squared of 2x, I can make use of the trig identity that 1 minus cosine squared of 2x is equivalent to sine squared of 2x. So now the integral that I'm left with is a trig integral that only involves even powers of sine x. There are no odd powers of sine or cosine. So in the event that we have only even powers of sine and cosine, we have to make use of the trig identities for these even powers. So in particular, sine squared of 2x is equivalent to 1/2 of 1 minus cosine of double the angle. So here, I had a sine squared of 2 times x. When I double that angle, I will have a 4x term here. So recall, like in the first part of this problem, we had rewritten sine squared of x as half of 1 minus cosine of twice that angle. So I took the argument of sine squared, I multiplied by 2. I'm doing the same thing here, but I now have sine squared of 2 times x. So that's equal to half of 1 minus cosine of 2 times 2x, which is where that 4x comes from. So now, if I take the constant of 1/2 and bring this out in front of my integral, I have a 1/8 times the integral of 1 minus cosine of 4x dx. So let's see what we have for this antiderivative. I have a constant out in front of 1/8, and the antiderivative of 1 dx would be 1x, minus the antiderivative of cosine 4x is 1/4 sine of 4x. And then, since this was an indefinite integral, I can include a constant of integration. Now, if I want to simplify a bit further, I could distribute the factor of 1/8 out in front, so that I would have a 1/8 x minus 1 over 32 times sine of 4x plus c. So in this first part of our lecture, we've considered how to handle integrals of products of powers of sine x and cosine x. And generally speaking, if we have one of our powers of sine or cosine of x as an odd power, we could factor out one factor of that trig function, either sine or cosine x, use trig identities to rewrite everything else in terms of the other trig function, say sine or cosine, and then make a u substitution. Or, as we saw in this last example, part E, what's a little trickier is if we only have even powers of sine and cosine. In that case, we have to make use of these trig identities involving sine or cosine x squared to rewrite our integral in terms of lower order powers of either just sine or just cosine.